Hi, everyone. Thank you all for being here today. And I especially thank the organizing committee and the scientific program committee for IISA 2022 for putting this event together. And I'm really sorry that I could not be there in person. And thank you to the organizers for letting me present my work virtually. So today I'm going to talk about new directions in Bayesian shrinkage for sparse and structured data. This is a joint work with researchers at the University of Michigan, especially Jonathan Boss, Brahman Mukherjee, and Jian Kang. So before I begin, here is a rough structure of what I'm going to talk about. I'll give a very quick overview of global local shrinkage prior, although you have already heard about some of this review from the earlier speakers in the session. And I'm then going to talk about grouped covariates, how to build a specially designed prior for these grouped covariates, their properties, applications, and some future direction. Okay, so before I begin, I just wanted to pause for a second and show you this pastures quadrant. And what it basically does is, so it sort of divides the entire body of scientific research into four quadrants, divided by whether it advances human knowledge by seeking a fundamental understanding of nature, or whether it's trying to uh, trying to solve an immediate problem. And I think that one of the beauties of statistical research in today's world is that it does apply uh, to both questions. It tries to solve, it tries to make use of knowledge, um, and at the same time, it is trying to quest for fundamental understanding. Okay. So you want to increase understanding and you want to build something useful. All right, so the motivation, and this is the immediate use part of this type of research. The motivation is the exposure correlation structure for NHNES data. Here, what you see is the correlation matrix, and if you look at these groups, we have 1, 2, 3, 4, 5 predefined groups. Some of these groups, like metals, have very weak correlation structure, weak pairwise correlation, and also heterogeneous effects. But if you look at some of the other groups, like the brominated diphenyl ether or the PAH, they have very strong pairwise correlation. So we want to build a shrinkage prior that can take into account this type of correlation structure. And we also want to build something that can adapt to bilevel sparsity, which means it might happen that not all the groups in a particular situation are relevant, and then within each group, not all covariates might be relevant. Okay. So this is our motivating example. Now, the canonical problems in high dimensional inference have been either the normal means, where you have a long vector of parameters theta, or a regression problem, the simple high dimensional regression problem, where you have more covariates than observation. And to learn in this regime, you have to put some structure on theta. For example, you can assume that theta belongs to an L0 ball of size Pn, where the Pn would be small O of n. So if you look at the proportional sparsity, it should go to 0. Okay. Now, the problem that we are trying to address today is a new direction in some sense. This is grouped covariates, where your y follows this generative model. We have C alpha plus summation x g beta g. These beta g's are our parameters of interest. We have capital G many groups of interest. The C alpha will include all the other effects that you don't want to put in these beta g's. For example, it could include BMI or age or socioeconomic status and so on. All right, so a brief overview of the global local shrinkage prior. The most popular in this family is the horseshoe prior, which has been quite successful and has spawned many close relatives, many global local shrinkage prior over the last 10, 12 years. So the idea here is that if you think about the most canonical problem of sparse normal means, the idea behind horseshoe prior is that you put a normal scale mixture on every theta I. So you have normal scale mixture with two parameters, lambda square and tau square. The lambda is a local shrinkage parameter, tau is a global shrinkage parameter. The local shrinkage parameter will try to identify individual signal, and the global shrinkage parameter tau would pull everything towards zero. The horseshoe prior will use the half Cauchy prior on both lambda I and tau. Now, one of the cool properties of the horseshoe prior is that if you look at the posterior mean coming out of this horseshoe prior, then it looks like a linear function of the observation yi. So it turns out if you compare this expression with the expression for a two-boost model, then this extra shrinkage factor works as if it's the posterior induction probability. Although formally it is not a posterior quantity, so we call this a pseudo posterior induction probability. So all we need for this horseshoe prior to work is that we need this shrinkage factor kappa pi to be 0 for large y, so that you don't shrink at all, or it to be close to 1 for small yi, so that you shrink a signal, you shrink an observation all the way to 0, right? A quick note here is that we can use the two-boost model, but it leads to a heavy computational complexity. So as I was saying, this has been very popular, and there are a bunch of variants of the horseshoe prior over the last few years, as you see on this table. They are alike, but not exactly similar, obviously. There are some differences in some of these interesting priors. Just to note, the similar structure in most of these is that, well, you have still a normal scale mixture with a mixing density on the scale parameters lambda I and tau, and they're typically heavy tail density to adapt for both for tail robustness and for controlling sparsity. Okay, the last two are special in the sense that they're motivated by count data, which is somewhat different from the continuous domain that we see usually. Okay, so this is how most of these pairs will look like. They should have a spike at 0, and they should also have heavy tails. Once again, the spike at 0 would promote sparsity, and the heavy tail will provide tail robustness, which means if your signal is large, then your posterior mean should be close to y for the normal means problem. So here is a demonstration of the tail robustness and sparsity. So if you look at this two plots, the first one is showing two of the candidates of this family, horseshoe plus and horseshoe, they have this characteristic U-shaped prior density, which will push the posterior mass near 0 and 1, unlike the lasso, which will push things near 0 somewhat, but not exactly has a spike at 1. And as a result, what happens for lasso is that if you look at this profile, this is yi versus theta I hat, so input versus output. And if you look at horseshoe, it will shrink near 0, but then as the signal grows larger and larger, it will come back to the diagonal line. So for a large observation, posterior mean should be close to the observation. But for lasso, there should be a vanishing, a non-vanishing bias in the tails, which motivates horseshoe. Okay. So for group shrinkage, once again, we have this situation where you have y coming from a regression problem, but you have your parameter vector beta is grouped into capital G many different groups. This XG is a matrix of standardized covariates in the G8 group, and beta, if you stack all the individual group parameters beta1 to beta G, it's a p/1 vector regression coefficient. Okay, so there is a grouped version of the horseshoe prior by Zhu et al. In 2016. What they do there is simply put another index for every group. So you have a normal beta GJ. So this is the simplest version. YGJ, GJ is the jth mean in the gth group. It follows a normal with mean beta GJ, which has a scale mixing, normal scale mixture. But the scale mixture will have a gamma G and a lambda GJ. There are two problems with this construction. The first is that it does not reduce to horseshoe prior for group size 1. So it's not a generalization. Okay. The second is more serious, that there is no hyperparameter to control how dependent the shrinkage is within a group. Right? So we need separate parameters to control within shrinkage and between shrinkage. So here is the key idea. Well, so we need a prior on gamma G and lambda GJ squared so that the product of them is a beta prime, which behaves like, which we can use for constructing a horseshoe type prior. So it follows from a result by Armagan et al. In 2013, and more recently Ray by Animal Ghosh, that if you take a gamma and an inverse gamma random variables, U and V, then the product UV would follow a beta prime distribution with parameters A and B. So this eta parameter is common, and this A and B are the two shape parameters for the gamma distribution and the inverse gamma distribution. So that leads us to this gig prior where we put the normal scale mixture. So you have still normal with mean 0. These are the scale parameter. Tau square is the global scale parameter. Lambda gg is the local parameter. Gamma g is the group specific local parameter. And then we put a gamma prior with AG and an inverse gamma prior with parameter BG on these two parameters. So that if you look at the product of these things, it will behave like a beta prime. Okay. One good thing about this type of construction is that if you look at the posterior distribution of the shrinkage factor, then it involves a term like the one highlighted in magenta. And it can be seen easily that if you make this parameter PG equals 1, so if the group size is equal to 1, then it reduces to an usual horseshoe prior. Okay. Now, how does this A and B parameter behave and what do they mean? So if you look at these two figures, so here, this is probably the most important plot of this presentation. So what is happening here is we are looking at two different observations, YG1 and YG2. YG1 is from a normal with mean beta G1. YG2 is from normal with mean beta G2. And you have we're looking at the plot of posterior mean of beta G1 versus the observation G1, right? So ideally, if YG is small, it's near 0, then the shrinkage profile should look flat. It should shrink all the way to 0. Then as you go away from 0, it should come back. So it should have tail robustness. The two colored lines here are for the two different values of the second observation. The orange color line is for 0. The blue color line is for observation 10. So what is happening here is, if for the first plot, if the two parameters A and B are both small, it does not matter what the second observation is, right? It doesn't matter whether the YG2 is 0 or 10. The shrinkage of beta G1 would be similar irrespective of the second value. For the second plot, where beta G is 1, which is going away from 0, then the shrinkage profile, they begin to differ. So here, if YG is small, if the second observation is also small, then you have a stronger shrinkage profile. The mean will be shrunk to 0 for a larger range compared to the second, which is YG2 is equal to 10, where it will be shrunk for a smaller region. So roughly speaking, AG, this parameter will control overall shrinkage. BG, this parameter will control within group shrinkage. Okay, we can also show that these properties would lead to some nice theoretical concentration properties. For example, we can show similar things as in the original horseshoe prior paper by us, where you can show that if YG is going to infinity, then posterior distribution kappa G should go near 0. If it's going to 0, then posterior distribution kappa should go near 1, which is what should discriminate between the signal and the noise. And we can also show some concentration properties for linear regression for p less than n. We can show if tau goes to 0, then the posterior distribution of beta hat OLS minus the posterior mean of beta would concentrate near beta hat OLS. And we can show posterior consistency for linear regression as well. Okay. Now, let's see how this works in simulation settings. This is two different situations. One is concentrated. So here each row, so the gjth box is jth exposure in jth group. So each row is a group. Each column is exposure in that group. So concentrated means that every group has the one exposure that is significant, that's relevant. Distributed, two groups have all the exposures relevant, but then they have three groups where nothing is going on. And we pick the correlation structure to be 0.8, the pairwise correlation within group, and 0.2 between the groups. Right? Now, let's look at how gig, this newly constructed prior, behaves in comparison with the other priors. So here, the first thing that we see here is that, okay, these parameters A and B does have some effect. So if you make them both small, which is what you saw in the figure a few minutes back, it would work really well for concentrated setting, but not so much for the distributed setting, right? Whereas if you make AG equals half and BG equals 1, it will do really well in this distributed setting, but will suffer in the concentrated setting. On the other hand, a very good middle ground would be this gig MMLE, which is basically you learn these parameters A and B via a maximum a marginal maximum likelihood setup. So you use empirical based estimators for these parameters A and B, and you can see that then it would work in both settings. It will be among the top 4 performers. Okay. On the other hand, a curious thing to notice here is that the spike and stub loss, so it will work really well for a concentrated setting. It is something that the spike and lasso does really well, but if you look at distributed, it suffers really badly. Same thing for Bayesian group lasso with spike and stub prior, works really well for distributed, but suffers in concentrated settings. Okay. So here is a real data example. We're looking at the NANES example, 2003-4. And so this is a study with 990 adults with 35 contaminants. And this is the correlation structure that we showed you before. So we have groups of size 3, 7, 8, 7, and 10. The first group, 3 metals, they have very weak pairwise correlation and heterogeneous estimated effect size. These two groups, PBDs in PAH, they have high pairwise correlation. Now, what happens? This is a comparison of the 4 different candidates. We have gig regression, we have linear regression, ridge regression, and the original horseshoe without any grouping mechanism. If you look at the metals now, which is where you have very weak correlation, then it turns out that, the gig regression does much better than linear regression or ridge. You have shorter credible interval, but there is not that much of a pronounced difference between horseshoe and gig, which is expected because of the weak correlation. On the other hand, if you look at, say, PAH or PBDE, what happens is that compared to the linear regression, you can obviously see the very long blue segment. That is what you get out of linear regression. And you can see that the length of credible interval is much shorter for gig compared to even horseshoe regression. Okay. All right, so here is a quick summary of this. So gig prior can customize the trade-off between group and individual shrinkage for each exposure class. This is the idea of bi-level shrinkage, that you need this trade-off between each class specifically. And we also believe that this correlated shrinkage is very important for grouped data where you have grouped covariates, because it will achieve additional variance reduction when you have correlation. If the correlation structure is weak and there is no grouping mechanism, then using a simple horseshoe prior will not be any worse. But in presence of grouping structure, extra correlation, this is useful. The other useful property of the gig prior is that we have closed form full conditional distribution for all model parameters, which is very helpful computationally. We can construct a gig sampler that can that's highly efficient. Okay. There are some future scopes for this type of work. One is that, so in theoretical section, we can show that the posterior distribution will converge near 0 and near 1 if either y goes to infinity or if tau goes to 0, which means that there is a possibility that it will still be oracle, which means it will have the lowest possible base risk out of all finite sample procedures in a decision theoretic framework. It needs to be established whether the gig prior would have oracle property. We have to also find the oracle risk for this type of problems. The other very useful future addition would be using this sort of grouping mechanism for other problems where you could have grouping structure, for example, multiple Gaussian graphical models. Right? And finally, I think that it is highly needed that we look beyond the Gaussian setup. For example, you can look at count data with either an overabundance of zeros or overabundance of small counts, or compositional data, or other discrete data structure where this could be useful. Okay, so thank you. This is a joint work with Jonathan Boss, Jin Wang, Jungying Park, Jian Kang, and Pramod Mukherjee. The manuscript is up on arXiv. By all means, please read it. And there's also the R package gig on CRAN. By all means, use it and let us know. Okay. Thank you. Thank you again to all the organizers and the audience for sitting through this. Thank you.